Transformations of polynomial functions is one of my favorite subjects in this chapter. It makes the diagrams start dancing, so it's a lot more fun. And plus, it's not that complex. We like the easier problems, don't we? So let's take a look. Even functions and odd functions. We went through this in a little bit in Algebra 1. It's still the same thing. So if the function hugs the y-axis, like in the first diagram, okay, when I do f of x, it's the same result as f of negative x on the same diagram. This function is an even function. But if like the second function in the middle, where f of negative x equals negative of f of x, then that's an odd function, right? So if you look at my input here, negative x here, I come out with negative f of x, which is the opposite of before I did the symmetric spin around the origin. So that's called odd. And there is a situation here where when it fails both of these conditions, when f of x doesn't equal f of negative x, and f of negative x does not equal negative f of x, that's when it's neither an odd function nor an even function. Here's an interesting example. It says, use the graph to classify the polynomial function. Is it even, odd, or neither? Now, from the look of it, compared to the concept page we just looked at, you can pretty much know that it's already an odd, right? However, we still have to prove it. So let's see. I'm going to reflect this red function around the y-axis, okay? Notice that that red point where it was y equals 1 moves over to the left-hand side. Y still equals 1, but at this point, the corresponding x value is negative 1. So in other words, when I rotate it over, that red line really should disappear, and the blue function remains. So I personally find this graph a little bit confusing. This is where technology doesn't help me, because after I rotate it around the y-axis, the red part really should disappear. Now, if the red part disappears, clearly it does not, it's not symmetrical around the y-axis. Therefore, this is not an even function. Okay, so the new graph, not even. Okay, now let's look at the second one. I'm going to turn off this, I'm going to turn off the reflection. So I'm making it go back to the original. And now let's look at what happens if I rotate it around the origin. I'm going to rotate this one. Oops, if I do this right. I'll rotate it. Look at that. Rotate it to 180 degrees. What happens there? What happens? It becomes the same graph. Which means I rotate around the origin, I became the same graph, and that means my f of negative x, I'll use a different color this time, f of negative x would equal negative f of x. Therefore, the new graph is odd. Okay? Here is something very similar, but now this time we do it algebraically. It's asking you whether this function is odd, even, or neither. You literally just, I usually have a picture in my head. If you're like me who like to think in terms of graphs and whatnot. So I'm going to find out if my f of x is the same as my f of negative x or not. Because this is an even power of 4, it definitely is the same, right? So because my f of x equals f of negative x. Therefore, my original function f of x is an even function. Pretty easy. Okay? I think there's one more exercise after this. Let's see. How does the transformed graph compare to the graph of the parent function? So this is an important exercise here. Let's look at this one. I'm given g of x equals 3x raised to the fourth minus 18. So for me to know how this works, I need to first find out what is my parent graph, right? So in this case, most likely, my parent graph is going to follow my quadratics. Really, if you think about x raised to the fourth is x squared squared, right? So you go from there, and I'm just going to open up the solution because it's not hard. Let's look at the first one is to identify the transformations. We already did that by finding out that it follows y equals x raised to the fourth, which is y equals x squared squared. So what that does is that it makes the function much wider than a quadratic function. And then next thing we're going to look at is the leading coefficient 3. What that does to the graph is that it makes the y value rise up much faster for the equivalent x values. So in other words, when the coefficient is a positive integer, it hugs the y value much tighter. Okay, that's how it rises much faster. Then finally, the vertical translation is a negative 18. You move the entire curve down by 18 units. That's how you get to it. Okay, now let's look at another example. If it let me erase this, yep, good. So in this case, it's not that much harder, to be honest. All it does is that it still has the same vertical shift. It still has the leading coefficient that hugs the y-axis much tighter because it's a positive integer. But this time it's adding a horizontal shift. So let's see, how do we treat that? So again, we identify the parent function as a cubed function. And therefore it's follows the y equals x cubed, right? So if you graph that first, then you do the horizontal translation. In this case, because it's minus 2, it's shifting to the right by 2 units. And so it becomes y equals x minus 2 cubed. Then the leading coefficient 5 will only make the function rise up much faster, 5 times faster. And then finally, you shift the entire graph upward to the north by 4 units. Exactly the same thing as what you would do in quadratic functions. You look at the leading coefficients, you look at the x horizontal shift, you look at the vertical shift, and then you're done. The given graph is a transformation of the parent cubic function or parent quartic function. How can you determine the equation of the graph? Now, since the ends extend in opposite directions, if you look at this, I'll use blue so that it's more obvious, right? Since the ends are extending to opposite directions, the end behavior shows that the parent function has to have an odd degree. So that would be y equals x cubed in our example here. But also because it's flipped the other way around, so it indicates that the end behavior is it's increasing as x is decreasing. So we know this leading coefficient is a negative number. So now I have y equals negative x cubed. Then let's look at horizontal shift and vertical shift. It looks to me what's happening here is this parent function went from here leftward by 3, downward by 1. So which means 0, 0 became, what did I say, leftward by 3. So it's negative by 3, downward by 1, which is negative 1. Okay, so if I put this into the vertex form, I would have negative x minus 3 cubed plus negative 1. If I simplify this, I would have minus x plus 3 cubed minus 1. So the function, if I want to write it into a function, this is my final conclusion here. Okay? Okay, the volume of a box in cubic yards, it's given by the function v of x equals x cubed. So in this case, x is yards and x cubed is cubic yards. The post office lists permissible shipping volumes in cubic feet. Write a function with cubic feet as the units. As someone who grew up with metric system, I really don't like these problems. However, this one is not too bad because we know 1 yard equals 3 feet. Okay, since we want to convert from cubic yard to cubic feet, so now that original x in yard becomes 3x in feet. So this new x is actually a foot. So 3x would give me the yard, and then my original x becomes, on the right-hand side, also becomes 3x. So that's 27x cubed. So my new function is v of x equals 27x cubed. And this represents cubic feet. So this is cubic feet. Okay? So here's a summary of what we covered in this unit. Probably the most essential information is how to define even functions. F of x equals f of negative x. And odd function is f of negative x equals negative f of x. That's the most essential information. The rest of it is all a review of parent functions as well as end behaviors. Remember positive leading coefficients versus negative leading coefficients. They give out very different, they place the graph in different places around the y-axis. As y increases, x increases, that's positive. As x increases, then y decreases, that's negative. And as well as translation, which you want to pay attention to how many units it shifts on the x-axis, how many units it shifts on the y-axis, and what does the leading coefficient do to the function. If it's negative, it flips it, right? It's for quadratics, it's a sad face. If it's positive, it's a happy face. Another thing to pay attention to is when you shift the x, make sure that the vertex form is a times x minus h rather than plus h. A times x minus h squared plus k in the quadratic example. Okay? I will see you guys soon. Bye.
Here's some iPhone hacks I guarantee you didn't know about, part 3. Go to the Notes app and click on Scan Documents. Now you're going to be able to scan anything into PDFs. If you make a mistake on the calculator, swipe left to delete. Tap and hold the timer button to set your timer much faster. When sharing photos with friends, click on Options and turn off location data. Send anyone your location on iMessage by typing I'm at.
I love this, especially the scan documents thing. So when you submit work, you can just press and hold the notes icon, and then you can scan the documents into PDF without buying any of additional apps. It's wonderful. All right, guys, see you later then.